we move on from where we left off yesterday. Let me reshare. Okay, so now you can see the slides. Participant, okay, hold on, yeah. All right, so let's continue. All right, so why is it important? Why do we have to discuss this? Fermi direct distribution function and all this stuff, the thermal excitation, the T1, T2. So why is it important? Location of EF or Fermi level or Fermi energy. Well, you may encounter Fermi energy and Fermi level. If you look at the definition, the Fermi energy is usually defined as the maximum point, the highest energy level that can be occupied by your electron at absolute zero temperature, at zero Kelvin. Okay, but on the other hand, Fermi level is applicable. Is the very same thing, but is applicable for a range of different temperatures. But Fermi energy is meant for absolute zero or zero Kelvin. So when discussing EF for semiconductor, so we're going to mention about Fermi level, right? Fermi level, because we need to see how the distribution of electrons and holes change across different temperature at different energy level as well. So the location of EF or the Fermi level within the material's band structure is important to determine the electrical behavior of the material. So we need to know the position of the EF because eventually it's going to affect the electrical properties of the semiconductor in this case. Later on, we're going to need to discuss intrinsic semiconductor, extrinsic semiconductor, where you dope different levels of holes and electrons in your extrinsic semiconductor or dope semiconductor. We're going to see what's the effect of the doping. And then we're going to move on into formation of PN junction and conductivity of your device and stuff like that. So when we discuss about the properties of the semiconductor material, before we even think about the joining of the P and N as a device, so we need to know how and to what extent does the position of the EF affects the properties of the electrical properties of the semiconductor. For insulator, the EF lies within a large band gap. So insulator is typically with EG of more than 4 electron volt. If you want to talk about the EG, usually for insulator, it's more than 4 EV. Then it's called an insulator, right? So, so in this case, you're talking about 5.5 EV, for example, for your band gap, then your EF will lie in the middle of your forbidden gap, which is 5.5 divided by 2. Okay. So metal, semi-metal, or the generic semiconductor, the EF lies within the localized band. Well, it depends on, because for your metal or semi-metal, even though they have slightly different properties, for metal, for example, since they have overlap of bands, so the EF is not it's not obvious because the bands are overlapped. Okay, so a large number of states nearby EF are thermally active and readily carry current, so they are there already and they are crossing the borders at all times. Whereas for intrinsic or lightly doped semiconductor, the EF is close enough to a band edge that they are there, that they are a dilute number of thermally excited carriers residing near the band edge. So if you're talking about intrinsic semiconductor, we're going to discuss later on, where you don't dope. If you discuss about intrinsic, the EF lies in the middle of your band gap. Okay, so this up here is your EC, down here is your EV, and EF is somewhere EG over 2. Okay, your band gap is this whole space of forbidden gap. So that's Eg divided by 2 will be your EF, right? So if you're talking about silicon 1.12, so that means your EF for intrinsic will be 1.12 divided by 2.56, right? Yeah, 0.56 electron volt for silicon, right? For crystalline silicon, it's going to be 0.56 as your EF for intrinsic silicon. And we're going to see later on when we discuss about extrinsic as your doping move into one direction. Either it's more p-type or it's more n-type. We're going to see that your EF is going to move accordingly, right? For intrinsic, we're going to see that your EF lies right in the middle of the band gap. But if you move to extrinsic, either for n-type or p-type, so we can actually alter the position of the EF across the forbidden gap, depending on the type of doping and level of doping. Okay. So in semiconductor and semi-metal, position of EF relative to the band structure can be controlled. So this is exactly what I said. We're going to discuss this in our next topic, intrinsic and extrinsic. So now let's go through DOS. What is DOS? DOS is density of states, right? So it can be defined as number of allowed energy states, per centimeter cube per energy interval. So that means you can imagine this as how big is the room available for you to enter and occupy. For example, if you imagine yourself as an electron and you and your friends, for example, renting a room, and you want to know how big is the size, right, of that room, so that you know how many can occupy. So the size of that room is pretty much similar to density of states. So how big is the room, and then you can decide how many of you can occupy that room, for example, or that dorm, for example. Okay, so it's a number of allowed energy states per centimeter cube per energy interval. And before this, we have discussed about this band diagram. Okay, so we have seen that this is your EV and this is your EC, and EF is right in the middle, especially when we are talking about intrinsic and undoped pure. Okay, is pure. So EF is equals to Eg over 2. To relate this to your density of states, or DOS can be graphically illustrated as this on the right. Okay, so what it means is you can also plot your energy axis on the Y, and then the density of states on the X. Okay, the X, then you can see the distribution is something like that. The profile looks something like this, and it only starts from the band edge. Okay, from both band edge of your conduction band at the top, and then your valence band at the bottom. So that means when an electron is excited into the conduction band, so say originally it's here and then it's then excited into conduction band, we need to know how much space is available, okay, or number of allowed energy states available per centimeter cube per energy interval. Okay, so this is how it looks like, and it goes infinitely into vertical direction, going up infinitely for the conduction band, and going down infinitely for the valence band. So going that way and that way at the same time. And this can be calculated by using this equation. If you want to know your density of states, or DOS, in conduction band, so that's given by NC, NCE, and all these parameters. We're going to see the simplification later on. So that is basically the equation that you need to use in order to calculate the density of states in the conduction band. On the other hand, if you want to calculate the density of states in the valence band, you need to use this equation below. Density of states in the valence band. So note that you need to use NC for conduction band and NV for valence band. right? So let's see how does it look like when it is simplified. Okay, let's look at this first, and then we're going to come to the simplification, right? So next stuff, just now we've covered about DOS, and then we need to know the probability of occupation, which is basically what we've discussed yesterday, before we come to calculating density of free electrons or density of free holes available, right? So what is then probability of occupation? This is exactly what we discussed yesterday. Probability that an allowed energy state, which is related to the DOS, is occupied by an electron. Occupied by an electron. And you can also do this for hole, right? It's just the opposite, right? The probability of this is given by Fermi direct distribution equation that we've discussed yesterday, which is basically this. So if you want to draw everything from the band structure, the one on the left here, and then you want to draw density of state that we discussed on the previous page. Now let me approve your friend here. And then probability of distribution, which is Fermi direct equation, which is this, just like what we discussed yesterday, where you got the step function at T0, and you got the curves smoothen out at increasing temperature T1, T2, T3, and so on, right? So that's how it looks like. And the distribution is governed by this equation, Fermi direct distribution, we discussed yesterday. Then, how do we then calculate our density of free electrons or free holes from the previous information, right? So this is the information needed. Then we're going to need to use this information in order for us to calculate density of free electrons or free holes. So density of free electrons, Ne, is defined as at an energy level of E, which is Ne. So it's given by the product, so that's the key, the product of your DOS, and your occupation probability, or probability of occupation. So what you have to do is multiplying your Fermi direct distribution function with your density of states in conduction band or valence band, right? So if you want to calculate your density of free electrons, you need to use N Fe times NCE. Or if you want to calculate your density of free holes, on the other hand, you need to use PE equals to 1 minus Fe, which is probability of finding a hole, times NVE, right? So it's just the opposite of what is shown here, right? So note that a hole is a missing electron. So a hole is a missing electron. So therefore, so if you want to put all of these illustrations together, so you have a band diagram here, and then you have your DOS here, and then you have your Fermi direct distribution function here, and then eventually all this information lead to your density of free electrons or density of free holes here. Okay, so what it means graphically, so what this equation means is this area will be the density of free electrons calculated from your density of states here, taken from here, and distribution of free electrons taken from here, giving this result, right? So on the other hand, if you want to calculate density of free holes, so you need to use your DOS information here. So this is given by NC here, this is given by NV here. So times this, and then you're going to get this, right? And for hole, it's given by the very same equation, but the reciprocal, or the opposite, where your Fe is now becoming 1 minus Fe because it's now whole, and your NCE becomes NVE because it's now whole, right? So, and your Ne becomes Pe. So you can see now the case for electron is number 1, and the case for hole is number 2. Okay. So if you zoom out, if you zoom into this region, so it looks like this. So it looks like this. So this is the zoom in version. If you zoom in version, sorry, not zoom out. If you zoom in version, if you zoom in into this region, the NC. So this is in the, if you want to draw the bigger representation, it's going to be something like that. The valence is here. So your NV will be down here. Your half, your EF will be in the middle, for example. This is just like that, right? Just a small portion of this DOS times your probability of occupation of electron. Okay, so this is the Fermi drag distribution function, and this is how it looks like, and it can be simplified like this. Okay, so this is the region where you have your electron, your free electrons in your conduction band. Okay, in your conduction band, and this is the result of the multiplication of this equation. So given by Ne equals to Fe times NCE. Yep, so that's giving you that. Okay, so on the other hand, if you want to go for your valence band or your density of free hole, then you need to shade the below region, then use the PE equals to 1 minus FE times NVE. Okay, so is it clear so far? Is it clear on how do we calculate the density of free electrons and density of free holes? Yep, straightforward, right? So what you need to do is you need to be able to represent the band diagram on the far left, and then draw the density of states, and then draw the Fermi drag distribution function at different temperatures, and then eventually your density of free electrons or free holes. Then you can see that all the information follow accordingly, right? So they follow accordingly. So it's easier for you to imagine and draw this way, because from this particular graphical representation on this page, you can know everything already. So what you need in order to come up with your NE or your PE. All right, so extra information: total free electron density or density of your free electron is the integral of all possible energies. Okay, all possible energies here means the energy above the conduction band H going up infinitely, right? It starts from the band H of your conduction band going up infinitely. So all possible energies that lie in between. On the other hand, it is also true for your valence band. If you want to calculate density of free holes, then all possible energies going down, right? All possible energy going down, for example, if you draw like that, infinitely. So all possible energies will lie from the band H of your valence band, which is here, then going down infinitely, right? All possible energies. So that's how you get it. So it can be simplified as, so if you want to do the integration, so this is how the equation looks like, and it can be simplified as this. Your N will be equal to NC exponential EF minus EC over KT, which is derived from your FE times NCE, and this is the simplified version. And then you can represent your NC in this equation by this. Well, you can do the calculation because you know the NC. We've gone through the NC equation just now. Yup, here. So you can just replace all the constant that you know, the effective mass of electron, a Planck constant, by whatever that you know, and you will be getting this 6.2 times 10 to the 15 times temperature to the power of 3 over 2 or to the power of 1.5 per centimeter cube. So that'll be your effective DOS in your conduction band, or NC value, right? So on the other hand, if you want to calculate the NV, so we've gone through the equation as well, so just replace all the constants, and then you will get this value, 3.5 times 10 to the 15 times t to the power of 1.5 per centimeter cube, and that will be the DOS in your valence band, right? So when you do the calculations later on, don't be confused when you want to use either NC or NV. right? So if you want to calculate electron, then NC. If you want to calculate the hole, then NV. Okay. It's also applicable for the calculation of your Fe. So if you want to calculate for electron, use Fe. If you want to calculate for hole, use 1 minus Fe. Right. So I've seen repeated errors done by students last time when they wanted to calculate a hole, for example, but they forgot to switch the NC to NV and Fe to 1 minus Fe, and they end up getting results that do not make sense. Okay. So this is the value that you have to bear in mind. 6.2 times 10 to the 15 times temperature to the power of 1.5, and 6.5 times 10 to the 15 times temperature to the power of 1.5. Right, so let's go through one calculation, for example. One calculation, and I'll leave the second example to you to try. So, calculate the probability that an energy state above EF is occupied by an electron. So calculate the probability that an energy state above EF is occupied by an electron. Okay, so if you want to draw this graphically, if you want to represent this graphically, where is the position of your EF now? Sorry, where is your position of your E on your Venn diagram? Anyone? Before you do the calculation, please draw the information, translate the information, translate the statement into a drawing or a sketch, and you will never go wrong. Okay? If you don't draw, if you don't sketch beforehand, and you jump right away to the calculation, you don't have the, you haven't translated your imagination into something tangible that you can see and cross-check. So always sketch something first, then only you jump to the calculation. Then when you get the result from the calculation, you can always make sense with the sketch. Okay. Sometimes when you just jump to the calculation, you at the end you may not be able to make sense of the results because there's no sketch to refer to. Okay. Physics is about giving giving meaning to the figures, right? So you get figures. So physics is about giving meaning to the figures. To be able to give meanings, you need to have some sketch, some drawing. And some even say that there is not physics when there's no drawing. No physics when there's no drawing. It's then just math, right? Okay, so let's do some imagination here. Let's do some sketch in your mind. So where we should draw your E based on this question? Anyone? You can unmute yourself before you do the calculation, because calculation is very simple here. But still, let's do some sketch. All right, I'm going to say above EF. So in this case, where is your EF? If you could draw your Venn diagram, yeah, well, you can explain now. So where would you put your EF to begin with? Might want to unmute yourself. Okay, go ahead. Half of EG, okay. So that means you first need to draw your, right, this is the very basic one, right? First draw your EC and EV. Never miss this. Okay, so now where's your EG? EF, sorry. Half of EG, right? Pretty much. So if it's silicon, then it's about 0.56 EV because the EG is 1.12. Okay, so now where's your E? Calculate the probability that an energy state above EF is occupied by an electron. So where is it? Is it on the upper part or on the lower part? Above here. I'm going to say above. Upper side, right? Okay, straightforward, right? Yeah, very straightforward. So anywhere above, for example, you can put it, you can draw a continuous band if you like. Okay. So let TB 300 Kelvin. So if normally the temperature is given, if it's not given, normally it's room temperature. Okay. So determine the probability that an energy level. Oh, this is the real question. Okay. So let T be 300 Kelvin. Determine the probability that an energy level 3 kT above EF is occupied by an electron. So energy level 3 kT above EF is occupied by an electron. So where would you draw the 3 kT? It's hard to demonstrate, right? Because we're not in physical class. Soalnya kalau dalam kelas, I'll just call any of you to draw on the board. So where would you draw your 3 kT now? Let's translate into sketch first, and then we do the calculation. The higher than the EF, right? Because it's energy level 3 kT above. Sometimes I find students cannot translate this statement into a mathematical equation. So, well, sometimes it's the simple question that kills you, right? So it's not necessary. You may do complex calculation, but you may miss simple calculation. So please beware. So energy level 3 kT above EF. So energy level 3 kT above EF. So that's 3 kT, right? And occupied by an electron. So you want to calculate the Fe of your electron, right? So let's go back to the Fermi Dirac distribution function. Very simple. So now we already know that E minus EF, so your E here minus your EF here is equal to the difference, right? 3 kT. So the difference is equal to 3 kT. Therefore, you just replace the E minus EF over 3 kT. Okay, so then the equation becomes 1 over 1 plus exponential of 3 kT over kT. Then what happens next? You just cancel out the kT, right? kT numerator and kT denominator. So then the equation becomes 1 over 1 plus 20.09. And your Fe now becomes 0.0474. So I said yesterday that you can either represent your answer in the form of this or in the form of percentage, right? So please get it right. So 0.0474 equals to 4.74%. So what does this mean? So it means that at energies above EF, the probability of a state being occupied by an electron can become significantly less than unity. Okay. If you want to relate this to your Fermi Dirac distribution function, and we've done the derivation yesterday, and you've seen that you can find electron with probability of 1, Fe equals to 1 with energy below EF, right? But in this case, the Fe is only like 0.0474 in comparison to 1 that we derived yesterday. So now what it means is it's significantly less than unity, or the ratio of electrons to available quantum states can be very, very small. Okay. And remember, this is at room temperature. So what do you think will happen at 500 Kelvin, for example? Anyone? What would you get, relatively, what would you get at 500, 600 Kelvin? Will you see your Fe increasing, or no change or decreasing? Probability will go up. Okay, why is it, Mushrik? Why is it going up? Why do you think it's going up? Yeah, I can unmute yourself. Go ahead. Anyone?
Doctor, because whatever energy, Doctor,
Okay.
whatever energy is available to boost this electron from the balanced conduction band.
Okay, so you said more energy available?
Yep, in higher radiation because it's higher temperature.
Okay, higher temperature, more energy. Therefore, you'll find more electrons in higher energy states.
Yep, that is a good chance.
Okay, all right, okay. Okay, Juaria, I think same. Okay, why do you think it is the same, Juaria? You can unmute yourself, go ahead. No change. Yeah, go ahead.
It's because from the equation T and T cancel each other.
Okay, you cancel each other. Okay, so that's the point. Okay, so you see, okay, Raihan also said no change as we cancel KT. Okay, that makes sense. So that will lead you to the calculation number 2, where you need to know, okay, now when you talk about comparing your Fe at higher temperature, for example, at 600 Kelvin, and compare that to reference. So now your reference is at 300 Kelvin, right? So your reference is now at 300 Kelvin at room temperature. So now we want to compare whether or not T at 600 Kelvin will generate Fe, right? But if you look at the equation there, you can actually cancel the KT, isn't it? Yeah, as said by Juaria and Raihan. But will the KT be the same at room temperature and at 600 Kelvin? What do you think? Okay, why is it different? KT is different, right? So this is what you have to watch out. Okay, this is what you have to watch out. You have to do referencing. Yes, it's different, right? Okay,
Yeah,
go ahead.
because we learned statistical mechanics, the higher the temperature, so the different it becomes the whole system. It becomes so the probability of occupying some state, it gets bigger and bigger and bigger in statistical mechanics. It was taught in third year.
Right. Okay. So if you do the calculation where it looks literally, it looks like KT cancel out, right? But then the KT is not the same to begin with. Right? So remember, if you want to compare your Fe at high temperature, you always have to know what is the basic, what's the reference first. Okay, for example, in this case, if the reference is at 300 Kelvin, so you then need to calculate your KT at 300 Kelvin, which is Boltzmann constant times 300, which will give you one value. And then if you do the very same calculation at 600 Kelvin, your KT product will be different, isn't it? So then in that case, you cannot simply cancel out because you need to compare your reference at 300 Kelvin. So that will bring you to the calculation number 2, where you need to repeat. I will just leave it to you to do later on. So you can see, I want you to try this, even though the answers are given. So you will encounter that if you repeat the calculation at higher temperature, you need to actually refer to your previous temperature reference. For example, if it's at 300 Kelvin, then you need to use a reference at 300 Kelvin. Then logically, if you give higher temperature or you're supplying higher energy, isn't it? High energy to the system, you will get more thermal excitation for the electrons. Okay, so you're supplying more energy. We discussed yesterday, when you increase the temperature, you are actually supplying more thermal energy to the system, and then you are actually supplying a higher energy to the electrons, and some of these electrons will be thermally excited to the higher band or conduction band in this case, right? So then if that's the case, then at higher temperature, since more and more electrons are excited to higher energy states or higher, in this case, the conduction band, then the probability of finding electron at that particular energy level should be higher than your reference. Okay, so I leave that case to you to do the calculation for example number 2, and we'll come back and discuss tomorrow. Okay, tomorrow 10 a.m. we'll discuss in our class on this calculation number 2. Right, so you'll see that you cannot simply cancel out because the product of your KT is different at different temperatures. Right, so I'll see you again tomorrow. Any questions for today? Is it okay so far?
Doktor.
Yep.
Dia nak kan apa tu untuk cari small letter E, small letter N and E.
Density of free electron
Yes, free electron
okay.
yang hole kan apa tu doktor dah assign untuk kalau untuk elektron pergi kat conduction band.
Okay.
Hole pergi dekat valence
Valence
band.
band. Okay.
Kalau nak cari elektron, density of elektron dekat valence band tak boleh. Ataupun cari hole density of hole dekat conduction band. Kalau kita buat terbalik, sebenarnya okay already.
Oh, okay. So, okay, the concept is simple. The concept is hole is a missing of electron. Okay, so then when we want to do the calculation of density of free holes, we'll come to the next topic anyway. When you want to calculate the density of free holes, you need to do in the conduction, in the valence band, because you need to relate to NV. When you want to calculate the density of electrons, you are actually referring to the electrons being excited. Okay, being excited. Okay, so therefore, that's why you need to relate your NE equals to NC times Fermi direct distribution function FE, basically NE FE, but for hole NV 1 minus E, 1 minus FE, right? But later on, when we discuss about extrinsic semiconductor in our next topic, we will discuss about majority carrier and minority carrier. So what it means is that if, for example, if I give you a silicon wafer, resistivity is about 1 ohm cm, and we have discussed before about the curve of resistivity against doping level, right? So that that translates into about 1 times 10 to the 16 per centimeter cube of, say, electron. If your silicon is n-type, so that means your silicon has 1 times 10 to the 16 of electron in that silicon as the majority carrier. So we'll discuss about the concept of majority and minority carrier. Majority means what is the carrier dominates that particular semiconductor material. Okay, the moment you have majority carrier, so or the moment you have n-type with 1 times 10 to the 16, that doesn't mean you don't have holes. So in that case, hole will be your minority carrier. So we'll discuss later on about law of mass action, where the product of n times p will be equal to ni squared, or n times p, the majority, the product of density of electron times density of hole at any time will be equal to ni squared. Ni squared is the intrinsic density of the carrier, which is equal to 1 times 10 to the 10 per centimeter cube for silicon, or if you square, so that will be 10 to the 20. So that'll give you, if you have, say, if you have your n is 10 to the 16, and your intrinsic is 10 to the 20 squared already. So to find the p, your p will be equal to 10 to the 20 divided by 10 to the 16, and your p will then be equal to 10 to the 4. So if you have your majority is 10 to the 16, your minority will be equal to 10 to the 4. If majority is 10 to the 13, your minority will be equal to 10 to the 7, because your NP is equal to Ni squared all the time. So we'll come to that later on. At this point, you just have to understand that the equation that we are using now is meant for electrons excited into conduction band, and therefore holes is left in the valence band, right? Valence band. So you don't confuse yourself with hole in conduction band. Well, that makes sense, but for the sake of calculation, just stick to the equation first, because later on we'll come to the concept of majority carrier and minority carrier. That will give you a bigger picture or better understanding of the whole concept. Okay. So by the way, good question, because you think about the why is not on the other side, right? Okay. Any other question? Ada? All good? Okay, so go back, try to attempt question number 2, even though the calculations are already given, it's okay. Try to understand and try to relate to the, what we discussed yesterday about the cancellation of KT and stuff, but you cannot do that when your KT is different. You need to calculate first. You cannot simply calculate when you know the values, right? So that will make sense in the calculation later on. So we'll discuss the calculation tomorrow in our next class, right? So see you again tomorrow, inshallah. Bye-bye. Take care. Assalamualaikum. Stay safe.
Thank you, Dr. See you tomorrow.
Yeah, inshallah. Bye-bye.